Hey pre-calc students, welcome to today's lesson on solving basic exponential and logarithmic equations. Now just a quick reminder that you should be doing all of these without a calculator. Okay, so there are three types that we're going to talk about today. Three types of basic exponential and logarithmic equations, and we're going to show you just a couple strategies on how to solve them, though they might not be the only way to solve them. You're always welcome to take a look at Khan Academy, Google, or YouTube to find other strategies if you would like. Okay, so the first type seem pretty basic. They are exponential equations. Notice that the x is the base. Okay, so the x is the base in these two examples. For these, we like to use inverse operations. Now, inverse operations specifically is the order of operations, but backwards, SADMEP. Now, normally you would check to see if there's any addition or subtraction, multiplication or division, etc. But notice that none of these, look at where the variable is. It doesn't have anything added or subtracted, multiplied or divided, but it does have an exponent. Now, the way that you get rid of rational exponents is you use their reciprocal, but you use it as an exponent. So if you have x to the third 3/4 power, and you raise it to the 4/3 power, so you do another exponent, but the 4/3, okay? And obviously it's an equation, so you want to make sure you keep the balance and do the same thing to the other side. The 3/4 and 4/3, because of properties of exponents, need to be multiplied. And 3/4 times 4/3 is 1. So you're essentially canceling the 3/4 and being left with just x. Remember, that's always the goal when solving equations. You want to find the value of x. Now, 8 to the 4/3 power, you need to do without a calculator. So for that, I want to remind you that we talked about a rational exponent rule in a previous lesson. So rational exponents are actually roots. The number at the bottom of the fraction is the type of root. And the number on top of the fraction, it could be a 1 or it could be any number besides 1. That's the exponent, okay? So the root is the denominator. All right, so that's going to help us over here. We need to simplify 8 to the 4/3. So 8 to the 4/3 is actually the cube root of 8 to the 4th power. So pause for a second and make sure that you understand how to convert from rational exponent to radical or root notation. All right, now the cube root of 8 is 2, and 2 to the 4th power is 16. So your solution here is x equals 16. Remember, feel free to pause the video and rewind anytime you need to review an explanation. Okay, so let's continue with that idea. If you have x to the 2/5 power and you use the reciprocal of that exponent, so you raise it to the 5/2 power, according to the properties of exponents, these you find the product of these. It's like a distribution property. 2/5 times 5/2 is just 1, so you're left with x. And then 4 to the 5/2 power, remember the denominator is the root. So you're finding the square root of 4 and then raising that to the 5th power. Okay, so it's really important for you to be able to kind of go back and forth from rational exponent to radical notation. Okay, the square root of 4 is 2, and 2 to the 5th power is 32. So the solution here is x equals 32. And that's just a quick summary of some basic exponential equations where x is the base. What about if you have exponential equations where x is in the exponent? In these situations, it's best to try to convert things so that they're all using the same base. All right, let's take a look at example number 3. We have e to the 2x power equals e to the 5x minus 3. According to the uniqueness property, if the bases are equal, and there's a base on the left and that's equal to a base on the right, then their exponents have to be equal. So they're essentially saying that 2x has to equal 5x minus 3. Okay, and that's based on the uniqueness property. So as long as the bases are the same, then their exponents have to be the same. But notice you can only have one on each side, one base on each side. So I'm going to set the exponents equal to each other, and then I'm going to solve. So solve for x. And for this, you're just using good old inverse order of operations. Now, you could have subtracted the 5x to both sides. It just depends on what your brain is more likely to do. But the correct answer here is 1. You can check your work by substituting 1 back into the original problem and see if you did it right. So 2 times 1 is 2, right? So you get e squared. 5 times 1 is 5, minus 3 is also e squared. A lot of people forget that when it comes to equations, you can always check your work. Okay, now for this one, it doesn't look like they're the same base, right? Notice that the x is the exponent. So this strategy of using same bases is whenever the x is in the exponent. That's a good strategy to try. So I'm going to go ahead and rewrite 81. So it has a base of 3. Now, it might take you a little bit of, thinking before you realize that 81 is related to 3, but if they're giving you a base, you should check if 81 is within that family of the base, right? So 3 to the first power, 3 to the second power, 3 to the third, 3 to the fourth. You can just make a quick list if you're in doubt. Okay, so 3 to the fourth power is 81. As long as the bases are the same according to the uniqueness property, then their exponents have to be equal. So you're essentially trying to find out, right, what the value of x is when 2x minus 1 equals 4. So add the 1, divide by 2, so x equals 5/2. And again, you can check your work. So 2 times 3/2 is 3. 3 minus 1 is 2. Where am I? Hold on. Oh, it's 5/2. I'm like, that's not going to work. There we go. That's why I like this, because you can check your work. Okay, so 2 times 5/2 is 5. 5 minus 1 is 4, and 3 to the fourth power is, in fact, 81. If you noticed, I previously had put 3/2 by accident, and I realized that was not going to work. But then I noticed my mistake, and I realized that it did work. So 5/2 is the correct answer. All right, so same thing here. If you come across a problem like this on homework or a quiz, an assessment, take a look. The x's and the exponent on both sides. Each side only has one base. Try to see if you could rewrite the bases so that they are the same. So I always kind of start by looking at the smaller one and say, can the smaller one be written, can the bigger one be written using the smaller base? Well, I just make a quick little chart. 6 times 6 is 36. There it is, right? I didn't even have to check 6 to the third. So I'm going to rewrite this as 6 to the 3x plus 2. That one stays the same. And I'm going to write this as 6 squared, okay, which is 36. But you cannot forget about the x plus 1 that was already there. And it's really important that you guys understand that this is a binomial, so you need to keep it in parentheses. So group the binomial, okay? Once the bases are the same, so I've got 6 and 6, okay, because previously they were not. So I have 6 and 6. The uniqueness property states that their exponents have to be the same. I'm a little off my game today, guys. Excuse me. Okay, so 3x plus 2 equals 2 times x plus 1. Remember, we already had the x plus 1 originally as part of the problem, so you want to make sure you keep it grouped because it was a binomial. I'm going to go ahead and distribute that 2. And then I'm going to solve. So I'm going to subtract 2x from both sides. Now this is basic Algebra 1 stuff, so you really essentially just need to show the work that you need. I know some of you guys can do some of this in your head. Okay, how can I check that I did it right? I can just substitute it back in and see if I get the same thing on both sides. So 3 times 0 is 0, plus 2 is 2, so 6 squared, and then 0 plus 1 is 1, and then 6 squared equals 36. So yay, we did it right. Okay, let's try a few more. So I've got 5 to the x minus 4 power, and I've got 1 over 25. Now, thinking as 5 as my base, right? 5 to the first power, 5 squared is 25. But notice I don't have 25, I have 1 over 25, so that means that it must have been negative. Because if the exponent's negative, drop it like it's hot. So I'm going to rewrite these as 5 to the x minus 4 as was given, and 1 over 25, I'm going to write it as 5 to the negative second power. Now, it'll take some of you guys a few, homework assignments to start to recognize relationships like that, but pretty much anytime you're given a fraction like this, like 1 over 25, and 25 is related to 5, then the exponent was negative. Okay, according to the uniqueness property, I can set the exponents equal to each other and then solve. So x equals 2. Remember, you can check your work. Sorry, that was supposed to be an eraser. Okay, put it back into the original problem. 2 minus 4 is negative 2, and 5 to the negative second power is, in fact, 1 over 25. So you remember you can plug in your answer into the original equation. In case you guys didn't notice, that's what I've been doing. Check your work. Right? Okay. Remember, at any time you are more than welcome to pause the video, do what you got to do so that you are understanding the lesson. Okay, 1 over 49 is the same thing as 49, except it's in the denominator, so it got dropped like it was hot. So I'm going to rewrite this as 49 to the negative first power, but don't forget there was already a binomial of 8 plus x. So I'm going to go ahead and write that in parentheses. Got another binomial on the right. The uniqueness property says that if the bases are the same, then their exponents need to be the same. And that's true for any time you have the same base on both sides of an equation, as long as those are the only bases. So one base per side. All right, I'm going to go ahead and distribute. And then I'm going to solve. So I'm going to add x to both sides. Add 4 to both sides. And then divide by 2. So notice that in this problem, I showed a little bit less work. But again, that's because, everyone does these differently. So depending on how your brain works, you might cancel the smaller variable. You might move the variables to the left side of the equation. Just depends. Remember, you can also check your answer by substituting it back into the original problem. Okay, 36 is within the family of 6, right? So 6 to the second power is 36. But if I want it written as a denominator, then that means that the exponent had to be negative. And this guy was already there, the 2x. It's not a binomial, but I'm just going to put it in parentheses just because I want to keep it together. All right, now the bases are the same. Great. So using the uniqueness property, I'm going to set their exponents equal to each other. Now, 2x is not a binomial, okay? So negative 2 times 2x is just negative 4x. And then divide by negative 4. If you want to check if you did it right, you can go ahead and substitute it back in to the original problem. Just keep in mind you should be doing this without a calculator. I know it's hard to resist the temptation of just grabbing the calculator and doing it there, but you don't want to build bad habits, so make sure you're not using a calculator. All right, when I look at the table for 16, it's not going to give me 64 because it just grows so quickly, right? So what I would do is I would say, okay, well, I try to see if 64 is within the family of bases for 16, or sorry, for the exponents, but they're both even, so maybe 2 or 4, right? If I think of those families, 2 or 4. So this problem could be done 2 different ways. You can use 2 as your base. 2, if you, right, think about it. Hold on one second. Sorry, kids. I'm like thinking out loud as I work. All right, so 2 to the 4th is 16, right? But 2 to the 6th is 64. So, and obviously, this is a process of just thinking through. So I could essentially rewrite these with a base of 2. However, I can also use 4 because 4 squared is 16 and 4 cubed is 64. So it's just a matter of whichever one you want to use. You can do it both ways. You can write it as 2 to the 4th power and 2 to the 6th power, or you can use 4 squared and 4 cubed. You will end up with the same answer. So you'd get 4x equals 6, divide by 4, and you get 3 halves. You'd get the same thing if you solve for x here. Notice that we would also get 3 halves. So it is possible to have 2 different bases. Like you could use 2 different bases as long as they give you the 16 and the 64 in this case and get the correct answer. So you have a little bit of freedom there. All right, now I always just try to see if the smaller one could be written, or the bigger one could be written using the smaller one. But as I think of my table of 4, right, with the exponential table, so I've got 4 to the 1st power is 4, 4 squared is 16, and 4 cubed is 64, so 32 is not on there. So then here I would try another base besides 4, like 2. They're both even, right? So try 2. 2 to the 2nd power is 4. So 2 to the 2nd power is 4. So I'm going to rewrite 4 as 2 squared. So 2 to the 1st power, 2 squared, right? I just did this list previously. And then 2 to the 5th power is 32. So I'm going to write 32 as 2 to the 5th power. But you can't forget about the exponents that were already there. These were binomials, so I'm going to make sure I keep them in parentheses. Okay, as long as the bases are the same, then you can use the uniqueness property to set the exponents equal to each other. Then distribute and solve. So again, it just is a matter of preference. Do you move the variables to the left, to the right? You always move the smaller one, so I'm going to actually add 5x to both sides. So add 5x because negative 5x is smaller than negative 4. Subtract the 18 and I get 2. Again, feel free to check your work by substituting the 2 back into the original problem. 27 and 9 cannot be written using the base of 9. So remember, we're not doing 9 times 3 or anything like that. We're doing the table of exponents. So you'd have to check if 9 to the 1st power is 27, 9 squared is not 27, right? And you essentially check, right, if you could use the same base there. So it can't be 9, but it could be 3. So 3 to the 1st power, 3 to the 2nd power, 3 to the 3rd power, there it is. So I'm going to go ahead and rewrite these as 3 cubed Don't forget there's already a negative x there, and 3 squared. Okay, uniqueness property says that I can set these equal to each other and solve. I'm going to go ahead and just multiply 3 times negative x. Distribute there too. I add 6x to both sides because I tend to move the smaller variable. And then divide by 2, or by 3, and you get 2. A lot of these problems are like puzzles. You just have to figure out how to rewrite them so that they have the same base. I really like these types of problems, but obviously any of you that are struggling with your exponential tables, all these little ones that I wrote in blue, I have some videos that I can share with you if you want me to remind you how to come up with these tables and do some of these problems without a calculator, okay? Just let me know. All right, the last type we're going to look at is just really basic logarithmic equations where there's only one log. These are very similar to some of the problems that we did in our previous lesson. So I tend to work better when something is written in exponential form. So if you're given one log, doesn't matter whether the variable x is your argument or your base. Quick reminder, when you're looking at a log, the little guy that's on the bottom right corner of the log, that's called the base. And whatever you're taking the log of, that's called the argument. So this strategy of converting it into exponential form is my recommendation whenever you have a single log. And again, doesn't matter if the x is the argument, the base, or the solution, the number on the right of the equal sign. All right, so I like to call this whoop whoop. So 64 to the 1/2 power equals x. So notice x is just whatever the 64 to the 1/2 is. Now I can rewrite 64 to the 1/2 as a radical, as a root, according to the rule that I mentioned at the very beginning of the lesson. So let me just scroll up. The rational exponent rule, right? In a fraction, rational exponent, the bottom is the denominator is the root, and the numerator is the power. Whoa. Beep, beep, beep. Okay, there it is. So 64 to the 1/2 is actually the square root of 6. Oopsies, I don't know why I wrote a 6 there. Told you I was off my game. Okay, square root of 64 and then raised to the first power. Well, square root of 64 is 8, and 8 to the first power is 8. So the solution here is 8. All right, so I'm going to do whoop whoop. X to the 4/3 power equals 16. Now notice that this looks very similar to the problems that we started with in example 1 and example 2, where the exponent is rational, it's a fraction, so I could raise it to the reciprocal exponent and do it to both sides. Now these are supposed to be multiplied, 4/3 times 3/4. It's a product property of exponents, and you get x to the first power. And then 16 to the 3/4, remember the denominator is the root. Just like the roots are always at the bottom of the plant. That's how I remember it. So the denominator, the one on the bottom, is the root, and then the numerator is the exponent. So the 4th root of 16, be careful, it's not 16 divided by 4, it's the 4th root of 16. So 2 to the 4th power is 16. So the answer here is 2 for the inner part, and then 2 cubed is 8. Okay, and then last but not least, I'm going to go ahead and do whoop whoop. So I got x to the 2/3 power equals 9. I'm going to use the reciprocal of 2/3, which is 3/2. So those cancel and give you just x to the 1st power. 9 to the 3/2 power is the same thing as the square root of 9 to the 3rd power. Square root of 9 is 3, and 3 cubed, you got it, 27. As always, guys, if you need extra help or have questions about this lesson, feel free to reach out to us on Remind or email. Have a good day.